Okay, in this video we're going to talk about linear regression. It is piggybacking off of the example we did for the correlation coefficient and scatter plots. So I'm going to use the same data that I used in section 4.1 example. This is the graph we had for 4.1, the correlation coefficient and the scatter plot. Now this line wasn't here. What we're actually going to do is calculate this line. So this line is called the least squares line. And what it attempts to do is create a pattern that would minimize the distance from each point in our scatter plot to the actual line. So we can move this line and we could possibly make it closer to this point, but as we make it closer to this point, it may be further away from some other points. So this line minimizes the distance to every point on here. And it's quite possible that none of the points we actually have are on the line. But it could be used to make predictions as far as if I had a 24-foot high tree or a 28-foot high tree, how many apples would be on it. Okay? So how do we calculate that? Well, you may remember from algebra, if you took much algebra and did graphing, the y equals mx plus b for a straight line, m being the slope and b being the y-intercept. The notation here is y equals a plus bx. You could call that bx plus a. But here the b is the slope. This is just a statistical term, very different from algebra, but the same type of calculation. And a is going to be our y-intercept. Okay? And this little symbol over y just says it is the least squares line. So for the slope formula, we have it here. It's the number of items times the sum of x and y's, minus the sum of the x's times the sum of the y's. So you may be familiar with m equals change in y over change in x from algebra. This is a change in those two variables on the bottom of the fraction. The number of items times the sum of x squared minus the sum of x and then square that total. The y-intercept, here we have the mean of y's minus our previously calculated b times the mean of x's. So keep in mind that x bar and y bar are the means that we calculated when we did mean, median, and mode, but just the mean. So we have a lot of these calculations already from the previous section. I did add in here the average of the x's. Remember, the x's total up to 180, and there were 10 of them. If you divide that, you get the average of 18. Also, the average of the y's is 162. So pushing that through the rate here to find the b, I get 14.07. Basically, that means that we get about 14 extra apples for every foot that the tree increases. Down here in the y-intercept, if I push that through, I get negative 91.26. That may be a good number for certain ranges. It may not, depending upon your example. But really, in this case, this means that if I had a tree that was 0 high, my trend line would land on negative 91. So that's not really realistic for this particular example, but it does give us a starting point. So if I plug in that a and b into my line equation, I get that the line of least squares is negative 91.26 plus 14.07x. So over here, I've made two graphs. They're really the same graph. In the previous example, I used the rescaled over here. Basically, maybe you can look at it and you can see that if I'm here at, where's a good place? 18. Okay, when my tree was 18 feet high, I got around 160 apples. That's what the line says. If I increase that by 1 foot up to 19, this here should be around 174, because remember, it's going up 14 for every 1 over we go. That's what the slope means. Because I had rescaled this to make it a little bit more visible, over here I did the same graph but started at 0. So I extended that trend line backwards because my software only used it for the data that was given. But if I follow it back, of course down here I see it hitting the axis, but if we was to follow it on down, we might see that it's somewhere in the vein of negative 100 if I went down to the 0 high tree. So this line could be used for for prediction. So I didn't have a 10-foot high tree, and maybe apple trees that are 10-foot high don't produce apples. But if it followed this model, we would predict that it would produce around 50 apples. But we could plug in for X any height for tree and calculate what we predict the number of apples would be based on that previous example.